the last class we were looking at the frequency response of a two-stage operational amplifier. This was the small signal equivalent, and we said that VO by Vi is nothing but the DC gain. What is the DC gain? It is GM1 R1 times GM2 R2. There is a right half plane 0, which is S CC over GM2, and this is the two poles are widely separated, and there is a dominant pole, and there is a, what do we call the second pole? And what was the dominant pole frequency? The dominant pole frequency is 1 over. The dominant pole frequency occurs at is due to the effective time constant at that node, and that is basically 1 over R1 times. Well, if you want to basically do the exact thing, it's a long expression, but in any case, since CC is a Miller compensating capacitor, the effective capacitance looking in at node Vx is for all practical purposes equal to Gm times Gm2 times R2 times Cc. There is a 1 plus Gm2 R2 there, but since Gm2 R2 is expected to be large, this is the dominant pole frequency, right. The second pole, right, is at this node, and at frequencies much beyond the dominant pole frequency, right. Pretty much you basically no current flows through R2, right, and no current flows to R1. So, the circuit pretty much looks like GM2 with a capacitive divider and feedback. The capacitive divider is that C1 and Cc in series, right, and so essentially GM2, the effective GM2 will basically be smaller. So, the resistance looking at that node is basically 1 over GM2 times, what is it? What is the effective resistance looking in there? 1 over GM2 times, yeah. So, basically there is what I mean, if I apply a B test here, right, what comment can you make about the voltage there, assuming R1 is open? Cc over C1 plus Cc times V test. So, basically the resistive part of the current drawn will be 1 over Gm2 times V test, right. So, that is so the this becomes 1 plus C1 over Cc. Okay. And the total capacitance looking, so this is basically Cc plus C1 over C, as Cc tends to infinity, this must be tending to 1 over Gm2. If Cc tends to infinity, what does it mean? Yeah, at high frequency, basically see if Cc becomes very large, then it is pretty much like shorting Vx with V test, and therefore the current that will flow will be 1 over I mean is Gm2 times V test, and consequently the resistance is going to be 1 over Gm. Is this clear? And the effective capacitance looking in is basically consists of two components. One is C2 and the other one is the series combination of C1 and Cc, that is C1 Cc over C1 plus Cc, okay. And therefore, this the second pole has a frequency which is we made a mistake or we okay? Oh, sorry, yeah, sorry, what is it? So, it is no, what is going on? Oh, yeah, sorry, this is Gm time Gm2 times Cc over C1 plus Cc and this times C2 plus C1 Cc over C1 plus Cc, and consequently this basically is Gm2 Cc over C1 C2 plus C2 Cc plus Cc C1, which is can be written as Gm2 over so omega d therefore is 1 over R1 Gm2 R2 Cc omega naught, the second pole is nothing but Gm2 over C1 plus C2 plus C1 C2 over Cc. Okay. So, if you want to have good phase margin, what comment can we make? How should we choose omega d versus omega naught? Omega d is very less than omega naught is a given, right? But is that enough? To achieve good phase margin, what should be smaller than omega naught? The unity gain frequency must be smaller than omega naught. It is understood that omega d is smaller than omega naught. All right. The unity gain frequency omega u, and what is the unity gain frequency? ADC times omega d, I mean approximately, right? And this is what is the ADC in our case? GM1 R1 GM2 R2 over R1 GM2 R2, sorry, CC, this must be CC. Okay. And therefore, what comment can we make? The R1 goes away, GM2 goes away, R2 goes away. So, almost unbelievably, it seems like the unity gain frequency is independent of, largely independent of everything else. It only depends on GM over CC. Okay. So, we will take a look at why this makes intuitive sense, going forward, but for good phase margin, omega u must be smaller than this, much smaller than omega naught. So, what is the trade off between phase margin and unity gain bandwidth? In any case, okay, so let us say omega u is much smaller than omega naught. What is the angle of the loop gain at omega u? Minus pi by 2. Why is this minus pi by 2 coming? That is because of the phase lag due to the dominant pole, right? And then you have is basically angle of ADC times 1 minus S over omega z over 1 plus S over omega d times 1 plus S over omega naught. Okay. So, evaluated at S equal to j omega, correct? And okay, and therefore, this is nothing but minus pi by 2 minus tan inverse omega u over omega naught. What about the numerator? Minus tan inverse omega u over omega. All right. So, the question is a quick question, does does the feed forward 0 hurt or help the phase margin? It hurts, right, because it is in the right half S plane, right, and what do you call, so we will take a look at it, so basically RHP 0 hurts phase margin, because it increases the effective lag of the transfer function at the unity gain frequency. So, to get a large phase margin, what should you do to, so for good phase margin, therefore, what is the bottom line? What should we choose? What would you ideally like GM2 to be? How do we increase phase margin? Omega naught is some GM2 over some blah blah blah, some capacitance, right? Omega z is GM2 by Cc. Yeah. So, basically to increase phase margin, therefore, GM2 must be increased, right. Okay. So, what is the trade off behind? If you go on doing this, what will happen? GM2. Okay. So, what happens to the unity gain frequency? How does it depend on GM2? Unity gain frequency, how does it depend on GM2? Independent. Okay. So, if you go on increasing GM2, the unity gain frequency remains the same and the phase margin keeps improving, and as GM2 tends to infinity, you would expect the phase margin to be 90 degrees. Okay. All right. So, but what is the price you are paying to get higher and higher GM2? Yeah. So, you need to pump more current, to be able to get a larger GM2, right. Another way of doing it is to increase the size as well as the current, okay. But the problem with that is that, well, if you increase the size of the transistor, the parasitic capacitances also increase, right. So, so basically, there is some trade off there, but the bottom line is that to increase phase margin, you will need to increase participation. Okay. All right. Now, a couple of things. As you know, there is a trade off between phase margin and the unity gain and the unity gain bandwidth. So, what do you think? And by the way, the unity gain bandwidth is basically the unity gain bandwidth of the op amp itself is GM1 over Cc, correct. So, let us say the op amp is enclosed in a feedback loop with a feedback factor f, all right. So, what is the loop gain function? The loop gain function will be this ADC times f times was 1 minus s over omega z divided by 1 plus s over omega d times 1 plus s over omega naught. Okay. So, what is the worst case feedback factor for stability analysis? When do we have, for what values of f would we have to be careful about stability? So, let us say all of this is exactly the same, none of that is changing. Okay. Because the op amp is the same, we are varying the feedback factor around the op amp, correct. So, for which feedback factor would we have to be most concerned about the stability of the closed loop system? And by the way, what is the useful range of feedback factors? What would how much would f vary in practice? If you are trying to build an amplifier, voltage amplifier, 1 plus R2 by R1 type system, it is 1 over f, correct. So, and you want to build an amplifier So, f must be less than 1, correct. So, the useful, I mean, if you are trying to build an amplifier, the useful range of f is 0 to 1. If you want to choose f equal to 4 like he suggested, you know what will be the closed loop gain is 1 over 4. If you want to get 1 over 4, I think there are smarter ways of doing this than using an op amp, correct. So, the feedback factors we have to worry about are basically f ranging from 0 to 1, right. So, in this range of f which is 0 to 1, where for what value of f would we be very concerned about stability. So, if f is 0, it is very clear that you know there is no feedback at all, correct. So, there is nothing to worry about stability, right. Okay. So, for higher values of so if you have actually followed any of the discussion, remember that the loop gain function, if you plot it on a this is log magnitude of the loop gain, this is the frequency, then what is this value? Yeah, that is 20 log ADC times f, okay. And then what is that breakpoint? Omega d. So, here it starts rolling off at 20 dB per decade, right, and this is then it starts doing at 40 dB per decade. So, this is omega naught, okay, all right. And so, what is the unity gain frequency here? It is ADC times f times omega d, okay, all right. So, now can somebody take a look at this plot and tell me what is the worst case feedback factor as far as stability is concerned? 1. Why? Yeah. So, basically remember that for the feedback system to be stable, the unity gain frequency must be as far away from omega naught as possible, right, for good phase margin. So, as f keeps increasing, what happens? It is approaching, the unity gain frequency is becoming closer and closer to omega naught, and therefore, the phase margin will decrease. So, in other words, equivalently the system is becoming getting closer to becoming unstable, right. Okay. If you know hypothetically, if you put a gain in the feedback path, right, the feedback factor, let us say, you know, I mean we listen to Abhishek and say we put a feedback factor of 3, what will happen? I mean the closed loop system will simply become, I mean it could simply become unstable, right, okay. So, so f equal to so for feedback factors you know less than 1, right, f equal to 1 is the worst case for stability, okay, right, for a dominant pole compensated op amp, okay. So, in many data sheets you know you will find the following description: the op amp is unity gain stable, right, okay. So, when they say unity gain stable, it means that it is stable even with a feedback factor of 1, okay. If an op amp is not stable for you know for a unity gain feedback, right, that does not mean much, right, if you are not going to be using it in unity gain feedback mode, right. So, let us say you wanted a gain of 50, right, you only care that the phase margin of the closed loop system is sufficiently high for that particular gain, right. It does not help you if the system is unstable for, I mean it does not you know help you if the system is stable for unity gain, right, nor does it hurt, okay, if it is unstable for unity gain, because you are not going to be using for unity gain anyway. Does it make sense, people? Okay, that is one point. The other one is you know this trade off between you know phase margin and unity gain frequency is pretty much like, you know, assume you are sitting on, assume, I don't know, you walk up, the new academic complex, which is like basically a very tall building, right? And of course, if you're at that height, there's a lot of, winds gusting. So, but if you stand on top of the, if you go onto the terrace, I don't know how many of you have gone there, but it's a great view, right? But then, there's always the danger of the wind pushing you over the, over the parapet, right? Okay. So, you can do, one of two things. You can be very conservative and say, I am going to stay 20 feet away from the parapet, because who knows, I mean, the wind may decide to just take me along, correct? Okay. So, what is the price you are paying for being, 20 feet under, behind the parapet wall? Well, you are missing, a great view, right? Okay. On the other hand, you may say, oh, this view is terrible, right? Let me go hang around, walk on the parapet, okay, right? And of course, now you get a fantastic view, but if there's a, there's a gust of wind, you might, right? You might just get pushed off the edge, right? And so therefore, if you have a wide, if you're, if you say I'll work with a very small phase margin, right, because I want wide bandwidth, which is analogous to saying, I'll walk on the parapet just because I can get a great wide view, right? Then, a small gust of wind will basically push you over the edge. In circuit terms, basically, if something changes, right? You thought these parasitics were something, or you missed a decimal point, and like, right? And therefore, parasitics all turn out to be, much larger. Then you will end up with interrupt. You understand? So, like standing on the top of a building, it's like it's a trade off. How far you're confident of, how close you want to go to the wall, right? So, if you are, if you like to play things very, very conservatively, then you will shoot for a very large phase margin and lose bandwidth. If you are, if you like to live life on the edge, right, then, you will say, okay, I will deal with, I'll have a 15-degree phase margin, and then, oh, now I get oodles of bandwidth. What do you call, but now I'm a lot more sensitive to everything, right? And this is a general principle in engineering. If you're pushing everything to the edge, right, to maximize performance, many times, it's not merely, the thrill of standing on the edge of a building, right? You're desperately trying to kind of push the limits of technology, right? And so basically, your margins are very thin, okay? And if margins are very thin, it basically means that, you are going to be in general sensitive to minor variations in everything, correct? And this is no exception. So that's one thing.